Okay, any questions? Now, the trick in this separation of variables, etc., is always the same. Just first choose a coordinate system in which the boundaries have simple expressions. Then assume your function is a product of functions of a single argument, sum all possible solutions, and then impose the boundary condition that you couldn't impose before. And already in spherical coordinates, we know the general solution. If you remember the general solution, well, I will give it also in the exam. So you can just start from that general solution, impose the boundary conditions, and you are done. Of course, you will need to identify your boundary conditions. They need not be always given as simply as, okay, the potential at this boundary is such and such. For example, in the last problem, you were given the electric field and asked to find the potential. If no questions, we will be starting the new subject. So let's start with the multipoles. Well, up to this point, most of the time we either have the charge distribution and we were talking about electric fields and potential created by that charge distribution, or we had these, let's say, these boundary conditions satisfied by the potential, and then we were asked to find the surface charge density, etc. But what about, for example, you want to calculate, study the electric charge distribution in an atom? Okay, you know that the potential should be 0 at infinity, but what about inside the atom? We don't really know anything. So we should be doing some experiments. So we will be, in the experiments, we will be able to measure the potential. So let's say that if you do some experiment and calculate the potential, and, well, let's say potential difference, but very far away, the potential should be 0. That's your boundary, one of the boundaries at least. So if the atom is, let's say, neutral, you will measure 0 potential. No potential. Okay, of course, with that knowledge, with those measurements, the only thing you can say is that the atom is neutral. But of course, then if you get closer and closer, or if, let's say, you are looking at an ionized atom, in that case, the potential will have such a form as you get closer and closer. Well, it looks like 1 over R. Well, if you go closer and closer, this is what you would expect, because it's ionized, it has a total charge, and if it's a point charge, then you know that the potential should decrease as 1 over R. But if you get closer and closer, 1 over R shouldn't go like this. But it might happen that what you observe is a behavior like this. It's not really 1 over R. So it's 1 over R plus some 1 over R squared. Well, this special term is what we call a dipole. So you see that this 1 over R squared is not just 0, from which you can guess that it's not a point charge, because a point charge shouldn't have that 1 over R squared. As you go closer and closer, well, this is how it should behave. But then you find that it has this behavior. Not really that 1 over R plus the 1 over R squared correction. So it behaves like some coefficient times 1 over R plus some other coefficient times 1 over R squared plus some other coefficient times 1 over R cubed plus etc. Then, of course, the more precise measurements you make, or the more closer you can get to your system, the more information you will obtain about the potential. So you can basically think this in terms of a kind of a Taylor expansion in 1 over R. So you would get you might get many terms. And so this is what we basically call the multifold expansion. So we don't know the charge distribution, but if you identify those coefficients appearing in this expansion in 1 over r, you can say something about what the charge distribution of your system is. So okay, this is what in real life we can actually do. I mean, if we have a system whose charge distribution we do not know and there are no principles that will allow us to determine the charge distribution, then the only thing left is you can make some measurements. And then let's make the theory, what these coefficients mean. So you see the potential at the point r, in terms of this unknown potential, we can always write it in this form. Rho of r prime divided by r minus r prime times d cubed r prime. Now, of course, this rho of r prime will be non-zero in this in a very small region if it's a localized charge distribution. And we are making measurements at a very far away point. Let's say that this charge distribution has some typical size, let's call it d. So this r prime will be less than d, less than or maybe equal to d at certain points. But this r is typically much larger than d. You see, if you just consider an atom, what's the size of an atom? The typical size of an atom? In terms of meters, let's say. No, that's too small. 10 to the power minus 10, typically. That's the typical size of an atom. Well, the devices that you use in the lab, what is the distances you can measure? Millimeters. Well, you see, r is typically of the order of millimeters. Let's say 1/100th of a millimeter. That would be quite precise. But the size of the atom is 10 to the power minus 10 meters. There are like 5 orders of magnitude. So this number, r prime over r, is typically much less than 1. So yes, here we have an integral. We have to calculate that one. But this r prime and this r vector, they are such that r prime over r, the length, are typically much, much less than 1. Well, if they are much, much less than 1, we can make a Taylor expansion. You see, 1 plus x to the power n. If you consider a Taylor expansion of this function for x small, this will be 1 plus nx plus n times n minus 1 over 2 x squared plus n times n minus 1 times n minus 2 over 3 factorial x cubed plus etc. So this is how it would go. Now let's look at this function over here. R minus r prime raised to the power minus 1. This is equal to r minus r prime squared raised to the power minus 1/2. And this will be equal to r squared plus r prime squared minus twice r dot r prime raised to the power minus 1/2. R is the large coordinate, so this is 1 over r times 1 plus x squared minus twice x times cosine theta to the power minus 1/2, where x is equal to r prime over r. X is very small. And the r hat dot r prime hat, this is equal to cosine theta. Theta is the angle between r and r prime. Or you can say that you can choose your z-axis to be pointing in the direction of the r vector. So theta is the theta coordinate of the r prime vector in the integral. So you are integrating over this theta in the integral. Now this function over here, you can expand this in terms of x, you can make a Taylor expansion of this function in terms of x. And that expansion will be equal to 1 over 2 sum over L x to the power L PL of cosine theta. Well, this is basically another definition of the Legendre polynomials. So if you just make an expansion of this factor in terms of x as a Taylor series in terms of x, the coefficients will depend on cosine theta, and the coefficients are actually the Legendre polynomials that we saw in spherical coordinates. So this is, besides the Rodriguez formula, this is another way how you can obtain the Legendre the explicit forms of the Legendre polynomials. Did you see the generating functions in 209 or 210? Generating functions. Well, this function over here is called the generating function of the Legendre polynomials. So now let's go back. Now we know the expansion of 1 over r minus r prime. V of r is equal to integral over r prime, rho of r prime, times sum over L, r prime to the power L, divided by r to the power L plus 1, PL of cosine theta. Well, we are integrating over theta. We are integrating over r prime. That's what this integral is about, but we are not integrating over r. So I can just take it out. So this will be equal to L 1 over r to the L plus 1, integral of d cubed r prime, rho of r prime to the power L multiplied by this Legendre polynomial. This integral over there is basically what we call a multipole, the Lth multipole of this charge distribution. So you see that the potential will be just a Taylor expansion in 1 over r. If you write it explicitly, let's say a couple of terms, V of r is equal to, if you look at the L is equal to 0 term, this is 1 over r, d cubed r prime, rho of r prime. We are looking at L is equal to 0 term, r prime to the L, L is equal to 0. L is equal to 0, P0 cosine theta is just 1. So the integral is just the integral of rho. But this is nothing but the total charge. This is called the monopole. That is called the monopole term in the expansion. Monopole basically corresponds to the coefficient of 1 over r. Well, you can actually see that the monopole is nothing but the total charge of my system. Now let's go look at the other term. L is equal to 1. This is 1 over r squared, d cubed r prime, rho of r prime, P1 is cosine theta, This is called the dipole. Well, basically the dipole moment is the coefficient of 1 over r squared plus the remaining terms. Now for us, for our future discussions also, it will be the dipole that's the most important for us, because when you talk about atoms or molecules, most of the time they are neutral, so they don't have this monopole contribution, but they will have a dipole. Either they will intrinsically have a dipole, or they will have a dipole when we apply an external electric field to them. And the remaining terms will be small. Remember here, our expansion parameter in this expansion is r prime over r, and typically this is of the order of 10 to the power minus 5. I mean, if you consider the analog, the example we had, the atom with the charge distribution of the atom, you look at the potential of the atom at a distance of 10 to the power minus 2 meters. So for such a system, r prime over r is typically of the order of 10 to the power minus 5, so that's very small. So the other, if the system doesn't have a monopole, it has a dipole, so this will be the dominant contribution. The next term will be just negligible, a factor of 10 to the power 5 smaller. So we can safely ignore them. So let's look at this dipole. Do you remember how we had defined the dipole? That was week 3. We had already discussed the dipoles. Well, that was a special case when we had a plus q charge and a minus q charge. Let's say this is the r hat vector. So the dipole moment we had defined in that case, in that special case, as q times d. D is the separation in the r hat direction. This was what we had, the way we had defined it. Now we have a more general definition. This is the more general definition of the dipole. Now let's look at it in a slightly different form. So this is the expression of the dipole. We will define the dipole vector. Now in that case, we only had 2 point charges. That was our simple dipole. But this definition of dipole is valid for any charge distribution, not necessarily just 2 point charges. Now this is nothing but d cubed r prime, rho of r, rho of r prime vector multiplied with the r hat vector. This is how we had defined this angle cosine theta. Cosine theta is the angle between the r prime vector and the r vector. So the general definition of a dipole is, the dipole vector is this one. This is the dipole vector in general. So that now the potential, you see, we are defining the potential up to the dipole terms at the point r is q over r. This is the monopole term, plus this dipole vector dot r hat divided by r cubed, or r hat divided by r squared, plus, of course, we have all the other terms in our expansion. So this is in the third week we had defined this, we had obtained this potential for a simpler system of these 2 dipoles. I strongly suggest you to review if you had forgotten. So this was basically the same expansion. It is still valid for whatever the charge distribution is.
Hocam şu integralleri hareket ediyor. Bu ışığın 2 tane yük arasında tüm küpleri süperpozisyon alsak bunu nerede ederiz?
Let's see. Well, I would rather go the other way around. This is the most general definition. Well, you see, this definition is valid even for a single charge. You see, for a single charge, we can define a dipole moment for a point charge, not necessarily 2 charges. But let's see if this definition would match our previous definition in that simpler case. So we have this plus q charge, we have this minus q charge. Let's say this is our origin. The position of the minus charge, let's call it r minus. The position of the plus charge, let's call it r plus. What's the charge density corresponding to this charge distribution? At the point r, well, it is almost always 0, except on 2 points. Well, we have one charge at r minus of magnitude minus q. We have another charge plus q at the point r plus. So this is our charge density. Of course, due to the properties of this Dirac delta, it is 0 almost everywhere except on these 2 points. And if you integrate this over a region that contains this point only, this charge only, you get minus q. If you integrate it over a volume that contains this charge only, you get plus q. So let's calculate the dipole moment. D cubed r prime, rho of r prime. This is our definition of the dipole moment. We just need to put in our charge density, q r prime minus r plus minus r prime minus r minus times the r prime vector. Well, the Dirac deltas are nice functions to integrate. So this is the 3-dimensional Dirac delta. If you consider a 3-dimensional integral, this term tells me that wherever I see an r prime, I should put an r plus. But there's only one place where I have an r minus. If you multiply it out, I can write it as 2 integrals. The first integral just gives me a q times r plus, minus the second integral just gives me q times r minus. This is q times r plus minus r minus. And that vector r plus minus r minus is nothing but this vector, connecting the negative charge to the positive charge. And this is actually how we had defined before the dipole moment. Let's look at the single point charge. Does it have a dipole moment? 0 dipole moment. Let's see if our definition tells us that it has 0 dipole moment. Let's say it is located at the point r0. What is the charge density? It will be a Dirac delta, 3-dimensional Dirac delta at the point r0. So let's calculate the dipole moment. Q times the 3-dimensional Dirac delta, r minus r0. But this is equal to q times r0. It's not 0. Which is kind of not nice, but nevertheless, it's non-zero. But there's another problem. What is this vector r0? What is it? Position relative to which point? Relative to this origin. But I'm free to choose my origin whichever way I like. I can put my origin over here, my origin over here, my origin over here. But if I change my origin, the dipole moment changes. I could have chosen my origin to be at the position of my charge. In that case, r0 would be 0 and the dipole moment would have been 0. So basically, the dipole moment depends on your choice of the origin. Now, we are not yet discussing the electric field lines yet. We will in a moment. But let's just stick with the definition for the time being. Then we will do the applications. Now, there seems to be a problem over here. It is the dipole moment depends on the choice of our origin. Let's see, how does it change as we change our origin? let me choose two coordinate axes. This is one. This is the other one. And let us assume we have some charge density over here. Let's calculate the dipole moment with respect to this origin and also with respect to this origin. Now, if I choose this, I choose a point in my charge density. Let us say this is the point R. This is the point R prime. And let's say this vector over here is the capital R vector, how much I displace my origin. And if you just add the vectors, you see that R prime is nothing but R plus the capital R. Now, the functional form of my densities will look different, at least in this coordinate system. If this is the x-axis, my charge density should be non-zero at negative values of x. In this coordinate system, my charge density should be non-zero at positive values of x. So functionally, they will look different. So let's say the charge density in this coordinate system at the point R should be equal to the charge density in the other coordinate system. Let me denote it by rho prime, because it will have a different functional form, evaluated at the point R prime. So basically, both R and R prime, they refer to the same physical point, and the charge density at that physical point should be the same. So this is why I have this equality. The dipole moment calculated in the coordinate system without the primes. Well, you see, this relation tells me that d cubed R prime is equal to d cubed R. So this is equal to, well, d cubed R is d cubed R prime. R vector is nothing but R prime minus the capital R. This is the small r vector. Instead of the small r vector, I use the R prime vector minus the small r. And then rho of R is nothing but rho prime of R, R prime. So the dipole moment in one coordinate system is equal to d cubed R prime, integral of R prime times rho prime of R prime, minus, I can take this R out of the integral because that's a constant, d cubed R prime rho prime of R prime. So the dipole moment calculated with respect to one origin is equal to the dipole moment calculated with respect to the other origin, but there is a difference that is proportional to the separation between these two origins, how much I shifted my origin, multiplied by the total charge. So basically, this tells you that the definition of the dipole moment depends on the choice of your origin, where you put your origin, if the total charge of the system is non-zero. So if the total charge were zero, then whichever origin you use, you would get the same dipole moment. So basically, this is why in the previous example of these 2 point charges, we didn't need to worry about the R origin because the system is neutral. Whichever origin you choose, you will get exactly the same dipole moment. But for systems like this point charge, the dipole moment depends on the choice of your origin. And if you change your origin, the dipole moment will change. And that is because your system is not neutral. So this is just a property of the dipole moment. It's not a problem, but it's just something to keep in mind. And furthermore, if you remember our motivation for defining these multiple moments, you see we started from here. we were assuming a small system, a small localized charge distribution, and then saying that, okay, so this is our charge distribution, but here we didn't really explicitly state it, but we assume that our origin is somewhere inside our charge distribution. So we pick the origin somewhere over here, and then look at the potential at a very far away distance. That is what we did. So that would be a wise choice of your origin. It should be somewhere inside your charge distribution, not at some other point. We can define the dipole moment, whichever origin you choose, but if the origin you choose is not really in the center of your origin, center of your object, center of your charge distribution, then this expansion over here, because if you are over here, you are basically saying that R prime takes large values. It cannot be 0. So your expansion will not converge fast. It will converge slowly. A wise choice will be at the center of it will be somewhere inside your charge distribution. Although you are completely free to choose whichever origin you want.
Ya orijinli charge'ın üstüne getirirsek o zaman pozitif olur.
True.
Bir çıkmaza giriyor.
No, there's no problem with that. You see, if you put the origin, you have a point charge, you put the origin right at the center. No problem with that. Remember, this was your expansion. So you put your point charge in the origin. This is the expansion. What this multiple expansion tells us that the potential at the point R, as long as you have some localized charge distribution and you are looking at the charge distribution at some point away from your charges, this can always be written as 1 over R to the power L plus 1 integral over d cubed R prime, let's say rho of R prime to the L PL of cosine theta. This is what the multiple expansion tells me. So if you have a charge at the origin, what is rho of R? Q times Dirac delta R. It is 0 everywhere except on the origin. But you see, when you are calculating this integral, well, the Dirac delta tells me that wherever you see this R vector, you should put the 0 vector. 0 vector has 0 magnitude. So if L is non-zero, well, you have some positive power of L, so this is 0, this term. Only for L is equal to 0, this is just 1. This is also 1. You have the integral of Dirac delta over R. So this is equal to Q times Dirac delta, Kronecker delta L0. So only the L equal to 0 multipole is non-zero, but that is the monopole. All the other multipoles are 0 if you have a single charge at the origin. So in this case, the monopole term is enough to tell us what the potential is of a given charge distribution.
Biz burada potansiyeli yaptık.
Now you see the potential we expanded in terms of multipoles. Monopole plus the dipole plus everything else. So L is equal to 1 term is the dipole. But L is equal to 1 term is just 0. So the dipole is 0. There's no dipole contribution.
John, what happened to the 1 over 4 by epsilon coefficient?
Good question. So it's here. And nobody asked me until the end of the second hour.
I thought it may be cancelled that with something else or
Well, at least you asked. The others didn't even ask it at the end.
Dersi iştahla dinlediğimiz için.
Other questions? Other things you forgot to ask because you were interested in the lecture so enthusiastically? Other things you thought were canceled by some magical factors?
Peki bir şeyin önemi var mı? Hani monopolün dipolünü hesaplamak için aksisin seçtiğimize göre bir hani farklı şeyler çıkıyor. Bunun bir önemi var mı? Yani
Well, it just tells you that you should kind of be careful in interpreting your results, especially for systems that are not neutral. It's just a fact due to our definition of the dipole moment. Now, we will be dealing with dipoles. Well, this is a simple dipole we have. So we have these plus Q charge, minus Q charge separated by a distance. And then we will make a definition of an ideal dipole. Ideal dipole is basically this system. And you take the limit as d goes to 0, q goes to infinity, q times d is equal to p constant. So a real dipole would have a finite size. It's the atoms, for example, they will have a dipole, they will have a finite size. But for idealization, if you cannot really measure the size of the atom, you can treat the atom as what we call an ideal dipole. It has almost zero size, or a size that you cannot measure, but nevertheless it has a finite dipole moment. Now for an ideal dipole, the potential is given by this expression. Well, for an ideal dipole, there are no other corrections. Now let's look at the electric field. What about the electric field that this dipole creates? It was one of your homeworks, right? Well, we can choose the z-axis to be lying along the dipole. So the v will be just p times cosine theta divided by r squared. Now the electric field is minus the gradient of the potential minus del over del r of p cosine theta over r squared in the r hat direction minus 1 over r del by del theta p times cosine theta over r squared in the theta hat direction. There are no phi dependence. If you take the derivatives, this is just twice p cosine theta over r cubed in the r hat direction plus 1 over r cubed p p times sine theta in the theta hat direction. This is the electric field. Which is equal to 3p dot r hat in the r hat direction minus p divided by r cubed. And let me add the 1 over 4 pi epsilon zeros. And this is how it will look. So we have the dipole over here in this direction. The electric field lines will just look like, well, they are kind of circular shapes. These are the shapes of the electric field lines. This is the direction of the dipole. Yes, any questions? Yes, this is the ideal dipole. It's sitting right over here.
Is it D goes to 0 case? Is it
D goes to 0 case. No, it's just we have 2-point charges, and then we take the limit that the separation between these 2-point charges goes to 0, and their charge goes to infinity, so that the charge, one is plus q, the other one minus q, and q times this distance remains finite. So for example, if you would consider a Gauss surface, imagine any Gauss surface that contains this point, the electric flux will be 0. As it should, because the total charge of the dipole is 0. This ideal dipole is 0. Okay, so see you tomorrow, and come with questions.